So this is just a little bit of practice on some of those Mathematica things. The first couple of Mathematica problems just involve defining functions. So a quick refresher on that. The function let's define is for the Boltzmann distribution with epsilon 0 equals to 0. So that ground state energy will assign to 0. And in that case, we get this form of the Boltzmann equation. And let's solve it for the population nj by just multiplying both sides by n naught. So n naught, that'll cancel n naught out here on the left-hand side. And we get this form of the equation. This is the result, and if I think about it as a mathematical function, this depends on the values of n naught, the values of e sub j, epsilon sub j, and the value of t. So again, in sort of mathematics notation, this is nj as a function of n naught, as a function of ej, and as a function of t. And that's what we're going to define in Mathematica here. So in Mathematica notation, I'll call my function nj just like here. So I'll call it n sub j. And again, square brackets for functions, so it's a function of n0. E energy j or something like that, or maybe energy, and t. I don't know. This one, we could put it as a Greek letter, but I'm going to avoid that just so I don't have to type that. And then to define a function, it's the colon and then an equals. And then I can just define it mathematically. So it's n0 times e to some power is exp. So exp negative, I'm calling this variable energy, over, and then kb times t. And here I was doing some Mathematica stuff already. Remember, kb is a constant, so I'll just define that up here. kb equals 1.381 times 10 to the minus 23. So there's my function. It's just one line. I can define it, and there it is. I should always check. If I take one of the examples from class, I'll just check that this actually gives the correct answer. I pulled this example from the book. For these values of the input variables, we get n1 equals 3.619 times 10 to the minus 19. So I'll try that out here. nj as a function of 6.022 times, and then caret 23. Energy is 2.0 to the minus 20, and t is 298. And let's just check that that gives us the right answer. I actually copied that down from the book wrong. It's 4.668 times 10 to the 21, and that does match when I actually grab the right number from our book. Now let's do one like this table function. So here you are supposed to get these table points for volumes and then pressures from the ideal gas law. Let's do for our example. So to do something similar, we'll make a table of values showing the temperature and the population in N1 for that same energy, 2.0 times 10 to the minus 20 joules, in steps from 10 Kelvin to 500 Kelvin with steps of 10 Kelvin. So this is now a table. And then remember, if you forget how to do this, you can do question mark table. So it's the expression, and then the version that's a nice simple one is I min, I max, di. So this is the variable, the minimum value, the maximum value, and the step. That's sort of the version of this we're going to want. So we'll do table, our expression. That's our list of ordered pairs. So the first value is going to be the temperature. The second value is going to be the value of our function nj, and we're going to evaluate it at n naught. I'll plug in 1 mole. Our energy is going to be this constant 2.0 times 10 to the minus 20. And the temperature is what's varying. So I've got a variable temperature here as the last argument. And I'll close my parentheses. Remember, you can always notice which parentheses or brackets are unclosed by looking at the color. So this is in that pink. It's waiting to be closed, and that's okay because I need a second argument here. So I've got my expression, comma. Now I need this, the variable. My variable that I'm varying here is t. That's what I'm varying as I change each sort of row of the table. and it's going from 10 to 500 in steps of 10. So t comma 10 is where I'm starting, 500 is where I'm stopping, and each of my steps are going to be 10. So I can do this. Let's save this to a variable. I'll call this like t populations or something like that. You can see it's all these data points. That's a lot of them. I don't really want to see it. But I've got a big list of them here. They all look pretty reasonable. I'm going to get rid of it, but the semicolon here, so I don't have to keep looking at it. The last piece of it was plotting it. So once I have the ordered pairs, I can just pass it to list plot. So list plot takes those ordered pairs, and we can see what happens here, right? So maybe I'll add some nice labels here, right? So the axes labels, the x-axis is temperature in Kelvin, and the y-axis is that population n sub 1 in moles. And so you can see for the last one here, we'll look at an example where there's a few more steps involved in your function. So in this case, it'll be nice to write your function so that you can wrap it in this module. An example that we can use is maybe if we wanted a function to convert the ways to probabilities. So remember, like from in class, we had these examples of like ways of A, B, C, D, and E. And let's say we have all these different ways we want to convert them to probabilities. So if you remember how we did that, we went in and first we had to take the total ways. So that was just adding everything up. Then once we have the total, just divide each of the ways by the total ways. So the probability of A is the ways divided by the total, the same for B, and so on and so forth. So a way to summarize that, you could say divide each ways by total ways. Now let's try to translate this to Mathematica. So the first thing to note is all these numbers up here we sort of treat the same. We first add them all up and then we divide each of them by the total ways. So a good way to do that is a list. So if we have basically, this is going to probabilities, so I'll call my function probabilities. And then first I'll just write this out sort of by hand. So first I have to say like the ways list would be equal to, I'll make all of these things into a list. This will be 5, and then 10, and then 20, and then 30, and then 5. I'll just make that list of the ways. Then the next thing I want to do is do the total. So that's the total function in Mathematica. So ways total equals total ways list. And I'll unsuppress it. So that's our 70, which matches. Then if I just want to divide each of these numbers by the total, that's actually just our normal division. So I can do the ways list divided by ways total. And that will divide each of these numbers by this total of 70. And that gives me this output here. Now to convert that to a function, I just want to package it up into this probabilities function. So probabilities, the input is the list of ways. So ways list underscore. And then the module, then what goes in here is the sort of intermediate variable that I needed. So that's this ways list was my input. Ways total was like that intermediate calculation that I did. And then on the bottom here in module, I do ways total. So that's my intermediate calculation. I end that with a semicolon. And then the last thing in this module is the output of the function. So now this is set up so that anytime I change the ways list, I can calculate a new probability. So I'll check that here. If I do probabilities of, and I'll just paste that list in, that gives me that same set of probabilities that I want. And let's say I had another ways that were 5. Now that changed them in what looks like the right way. I could also check it with one where I know, like if I did 5 and 10 ways or something, that's 1/3 and 2/3.